Welcome back. I'm Muggsy, and today I'm going to explain scientific notation. All right, let's start with the problem. What's the top number compared to the bottom number? Is it bigger? Is it smaller? I don't know. At a glance, I can't really tell. I just see a bunch of zeros, and that's really confusing to me. Scientific notation, though, will allow me to tell the difference between these numbers quite easily. Furthermore, I can even perform arithmetic with these numbers really easily. I could say, what's the top number divided by the bottom number? But before we do that, let's just briefly explain what scientific notation is and what it's useful for. I remember when I was a student, I was really confused about scientific notation. I didn't really understand how to use it or why to use it. It seemed really like a bunch of extra steps. Like, why couldn't we just use the decimal system? Scientific notation, though, is really simple. I can explain it using two words: scientific and notation. It's scientific in the sense that we use it in the sciences a lot, and it's really useful. And the further I went in my scientific career, the more I used it and the more I really got comfortable with it. And eventually I got to the point where I really preferred it over using a bunch of zeros. And that's because in the sciences, we measure really, really big things, like the distance between two stars, or really, really tiny things, like the mass of a cell, or a molecule, or an atom, or even a subatomic particle. The other thing about scientific notation is that it's notation. What that means is it's just a way of writing things down. When you put a number in scientific notation or take a number out of scientific notation, you're not transforming that number at all. And in fact, you can always check your work because a number in scientific notation should always equal itself in decimal notation. Just like writing 20 in decimal notation is the same as writing XX in Roman numerals. These two things are the same. We're not transforming the number, we're just using two different notations, Arabic numerals and Latin numerals, to just demonstrate this 20. If I were to use scientific notation, that would be 2.0 times 10 to the first. It's the same thing. Okay, so now, what's this thing I just did? That's scientific notation. And in this case, it actually seems really stupid, because why would it's much simpler to just call this number 20 in Arabic numerals than to use Latin numerals or to do this thing with exponents and all that. And I agree with you. That's kind of stupid, and I don't like to use scientific notation for really small numbers like 20 or 5 or 1.2 or something like that. Where I do like to use scientific notation is for these really, really small or really, really big numbers. Okay, so how do you put a number in scientific notation? In order to put a number in scientific notation, all that needs to happen is the number needs to be, or the coefficient, I guess, this number in front, needs to be between 1 and less than 10. So greater than or equal to 1, less than 10. It can just be one digit big. And that means the decimal point needs to be after the first non-zero digit. So for this number, I'm going to move the decimal point 1, 2, 3, 4, 5, 6 times until it's right after that first non-zero digit, which is the 2. Okay, so then my number becomes 2.4. And now remember, I'm not actually changing my number. So 2.4 is not equal to 0.0000024. So in order to make these numbers the same, I need to account for all these decimal places. And the way that we do that is by using powers of 10, because each decimal place is just a power of 10. Okay, so I moved it 1, 2, 3, 4, 5, 6 times. So this is going to be 2.4 times 10 to the 6th, although I think I just screwed up, because 0.000024 is not the same as 2.4 times 10 to the 6th, or 2.4 million. And so when you're dealing with these zeros that are in front of the first non-zero digit, they're actually, you actually have to use a negative exponent. So this is 2.4 times 10 to the negative 6. This value in scientific notation, 2.4 times 10 to the negative 6, is exactly equal to this value, 0.000024. Okay, I know that was a lot. We'll go over quite a few more examples so you really get this. Let's do this bottom number. We're going to take the decimal point here and we're going to move it so it's after the first non-zero digit, which is this 6 over here. So we're going to move it 1, 2, 3, 4, 5, 6, 7 times. So we're going to have 6 with nothing after it times 10 to the negative 7th. And again, this is negative 7 because I'm moving those decimal places to the right. I'm essentially making my number bigger. 6 is bigger than 0.000006. And so I need to make my exponent smaller. It becomes negative 7. If I were going the other way, as we'll see in the next example, I would make my exponent bigger. Okay, so now remember those problems I had for you at the very beginning of this video. Which of these two values is bigger and what's the top value divided by the bottom value? Well, here it's really easy to compare. Negative 6 is bigger than negative 7, so this top value is the bigger one. Likewise, I can actually do the division really simple. Now this I'll show you in a later video, but I'll just do it right now in kind of a brief form. This basically becomes 24 times 10 to the negative 7th divided by 6 times 10 to the negative 7th, which is 4. The answer is just 4, a really simple answer. That requires a little bit of wizardry, and again, I have another video on how to perform operations in scientific notation. You can watch that later. Right now, we're just going to focus on how to put a number in scientific notation and how to really understand what scientific notation is. Okay, let me give you a few more examples. Okay, here I have 4 numbers, and we're going to go ahead and put these numbers in scientific notation if they're not already in scientific notation. We're going to start with this top one. Looks like 1.2 million, right? Meters. That's a really big number. To put it in scientific notation, again, all we're going to do is we're going to move the decimal point until it's right after the first non-zero digit, which in this case is the 1 in front. Now, where is the decimal point? I don't actually see a decimal point here. These are commas. Well, if there's no decimal point, you always know the decimal point is at the end of the number. And it's implied that there are some zeros here, although they probably weren't measured. That has to do with significant figures. I have a video on that. So let's take that decimal point at the end of this number and let's move it until it's right in front of right after this 1. So we're going to move the decimal point the other way now to the left. We're going to go 1, 2, 3, 4, 5, 6, and there we go. It's right after the 1. So we end up with 1.2, and then you can either include these zeros or not include these zeros depending on what you know about significant figures, times 10 to the 6th meters. And now this number is in scientific notation. And again, remember, it's just notation. We're not transforming this number at all. This number is exactly the same as that number. It's just a different way of writing it down. And you can see why some people might prefer scientific notation. In many ways, this is a cleaner, simpler number without all those zeros. And as you saw in the previous examples, I can do math with this actually a lot easier than I can do math with this big number with a bunch of zeros. Okay, let's look at the next example. What's the first non-zero digit? It's this 5 right here. Where's the decimal point? It's right here. Let's move the decimal point until it's after the first non-zero digit. 1, 2, 3. Okay, now we have 5.0, because that new decimal point's right there. Now remember, this time, times 10 to the, we moved our decimal point to the right. And so therefore, we need to make our exponent smaller. So instead of being 1, 2, 3 times 10 to the 3rd, it's the negative 3rd. We made our number bigger. We went from 0.005 to 5. So we need to make our exponent smaller to balance that out. Negative 3. 5.0 times 10 to the negative 3. Let's look at the next example. 5.2 grams. What's the first non-zero digit? 5. Where's the decimal point? Right after the first non-zero digit. So this number, when in scientific notation, is just 5.2 grams. It's already in scientific notation. Now, I often get students that say, well, doesn't it have to have like an exponent times 10 to the something? And the answer is no. A number can be in scientific notation without any exponent as long as the decimal point is right after the first non-zero digit. Take a look at all of these coefficients. That's just the number in front for all these answers we just did. And you'll notice all of them, 1.2, 5.0, 5.2, are numbers that are greater than or equal to 1 and less than 10. They're all single digit numbers, 1.2, 5.0, 5.2. And so that's just the secret. Any number in scientific notation, the coefficient, the number in front, is just between 1 and 10. So since 5.2 is between 1 and 10, it's already in scientific notation. So this one's done. Now, you could use exponents. You could say this is 5.2 times 10 to the 0, because 10 to the 0th power, anything to the 0th power, is 1. So 5.2 times 1 is just 5.2. But to me, that just is a little bit silly. It's technically correct, works just fine. Maybe you need it to do math. But whenever you can, I would say just keep the number as it is, 5.2. That makes perfect sense. Okay, 9 liters. Let's put that in scientific notation. Check, we're done. 9 is between 1 and 10. Where's the decimal point? Right after the 9 there. Where should it be? Right after the 9, which is the first non-zero digit. So that number's already in scientific notation. Again, these last two problems were basically trick problems. A lot of numbers, if they meet the criteria that I explained previously, are already in scientific notation. You don't need to do anything to them. They're the same in decimal notation as they are in scientific notation. Let me give you one more example. Let's say you have 50 and you want to put that in scientific notation. That one gets a little bit goofy because, again, the decimal point's here. We're going to move it 1 point until it's right after that 5. So it becomes 5.0 times 10 to the, we moved the decimal point 1 space. We moved it to the left. We made our number smaller. 50 became 5. So our exponent needs to get bigger. They're always opposite. So this is 5.0 times 10 to the first. This one just seems a little bit goofy because it's weird to use scientific notation for such a simple basic number like 50. And also to my mind, and probably to your mind as well, 5.0 times 10 to the first seems like a kind of a more convoluted and complicated way of writing this number than 50. But regardless, your teacher might ask you to put a small number like 50 in scientific notation. This is how you do it. So just to recap, what is scientific notation? It's scientific. We use it in the sciences because we measure things that are really, really small, like 0.0000000 grams. And instead of saying all those zeros and writing out all those zeros, we can just say, I forgot the number, 5 times 10 to the negative 23rd grams. And then it's notation. It's just a way of writing numbers down. It'll never transform your number. So in all these examples we did, the number in decimal notation and the number in scientific notation are the same. They've just written different ways. We haven't made the number bigger or smaller or anything like that, because whenever we made the number bigger, we made the exponent smaller. And whenever we made the number smaller, we made the exponent bigger. So they always equal out in the end. There's a lot to dive into here. I suggest you kind of get started with some problems. You'll get the hang of it real quick. And as time goes along, I think you'll get really comfortable with scientific notation. And hopefully you'll see the immense advantage of it as I do. I'll catch you next time.